All right, welcome back to another calculus lecture. In today's lecture, we are going to begin our trek through the various applications of the derivative. So up to this point, we've spent a lot of time focusing on how to compute the derivative and how to interpret what the derivative means. And now what we want to do is actually start applying the derivative to problems that might arise in the actual world. Also, fun fact, I recorded this entire lecture once before and then realized that my mic was unplugged. So round two, here we go, fun stuff. So I think probably the best way to begin this is to write out an example problem, sort of a quintessential problem that has to do with related rates, and then kind of talk through a procedure and sort of outline a procedure for solving these kinds of problems. So our first example, sort of classic related rates problem. So a 5-meter ladder leans against a wall. And the bottom of the ladder is 1.5 meters from the wall. When it begins to slide away from the wall, at a constant rate of 0.8 meters per second. Okay, so how fast is the top of the ladder sliding down the wall one second later? Okay, so the scenario that I've got, if I make a sort of crude setup here, if my purple pen is the ladder, then I've got my ladder leaning against my wall, and then it begins to slide and fall down. And it slides at a constant rate. Okay, so how do I figure out the velocity of the top of the ladder after 1 second has passed? It seems like, you know, I've got a lot of information to parse through here, and I've got a lot of quantities and you know, a speed here and this time factor that I need to think about. So how do I sort of get started in solving these problems? So let's go ahead and just outline a procedure for solving these problems. So steps for solving related rates problems. So the first step that we want is going to be 5 steps. So the first step that we want to do is just give names to things and draw a picture. So name variables and draw a picture. So maybe I might say the bottom of the ladder, the distance from the bottom of the ladder to the wall is 1.5, and then its velocity is 0.8 meters per second. I might say this is like x and this is dx dt or something like this. So we want to name those variables so that we can actually sort of work with them mathematically as symbols, and then sort of draw a picture to inform our intuition about what's happening in our problem. The next step is to state known and unknown quantities and or rates. So rates being the rates of change of these quantities. So here I'd want to say that my distance from the bottom of the ladder to the wall, so my x is 1.5, and then dx dt is like 0.8 meters per second or something like this. Next step is the really key step here. We want to find an equation or relationship between the quantities. So here I've got my example problem. I've got the height of the ladder and then its distance to the wall, or its vertical distance away from the ground, and the horizontal distance from the wall. And then I need to come up with an equation which is relating those two things. And this is typically going to be some sort of geometric relationship. So as we'll see, we're going to use the Pythagorean theorem here. And we might also use the volume of a sphere, the area of a circle, the definition of tangent. We'll do an example with that one. But really, the picture should help to inform your intuition about the geometry of the problem and what sort of equation or relationship we need to use. So once we've found that, what we can do is we can differentiate it and when I say differentiate, these quantities that we're interested in, so here my quantities depend on time. They are changing as time elapses. And so I can differentiate with respect to time or with respect to whatever independent variable I have, and then relate the rates of change of these quantities together using this equation that I found here. This is going to be very reliant on the chain rule, a proper application of the chain rule in order to get these derivatives and these rates of changes coming out properly. Okay, so differentiate to relate the rates. And then once we've got this relationship, we can substitute known quantities and rates. To solve the problem. So once we've sort of set up the problem in its entirety, we just need to input the information that is given to us in the problem, and then we can make our conclusion about the problem. So these are the 5 steps that we're going to use. Let's go ahead and just apply them in this first problem, this classical ladder problem. So first thing I'll do is go ahead and draw a picture to get an idea of what's happening. So I've got my wall, and then the ground, and then I've got my ladder leaning against the wall. Maybe we'll put some rungs on it. And I've drawn my picture, and now let's put in some information we know. We know that its length, it's a 5-foot ladder. And then we also are interested in this horizontal distance and this vertical distance. So let's call those X and Y. Okay, so step 1, X is going to be distance from wall to bottom of the ladder. And Y is going to be equal to the distance from the ground to the top of the ladder. And we should note that X is a function of time. So we'll let T be time here. So X and Y both depend on time. They are changing with respect to time. That is, we can differentiate them with respect to time. Okay? So we've got our setup here. Let's go ahead and write down what we know and what we don't know. So we know that, well, I know that at time 0, I am 1.5 meters away from the wall. So X of 0 is 1.5 meters. And I also know that this is moving away with a constant rate of change of 0.8 meters per second. Well, what is that with respect to X and T? it is precisely the derivative. It is the rate of change of x with respect to t. So dx dt is equal to 0.8 meters per second. And what is it that we want? Well, we want the rate of change of y after 1 second. So we want dy dt, and I'll use this notation, evaluated when t is equal to 1. So this vertical line here just means I want the derivative evaluated when t is equal to 1. Okay, so that's what we know and what we don't know. Now what we need to do is relate these quantities together. So as I mentioned before, we can use the Pythagorean theorem for this because we have a right triangle. So I know that x squared plus y squared is equal to 5 squared. And I think it's important, maybe let's reiterate the fact that these are actually compositions of functions. So I'm taking this function of t and squaring it. And same thing with the y of t function. Okay, I've just said the same thing here, but just included this extra notation to emphasize the fact that these are functions of time. They're not just their own variables. There's this third parameter, time, in the background, which is sort of governing what's happening. Okay, so there's my equation. Now, let's differentiate it with respect to time. So d dt of x of t squared plus y of t squared. So we're going to differentiate each side of this equation. One side is fairly easy to differentiate. We'll do that in a moment. So if I want to differentiate this equation, I have to apply the chain rule. So I differentiate this outside function, which is the squaring function. So I'm going to get 2. I plug in the inside function, and then I multiply by the derivative of the inside function. So derivative of the outside function, plug in the inside function, multiply by the derivative of the inside function, and then same thing with y. Okay, and then of course the derivative with respect to time of 25 is just 0. That's a constant. It doesn't change with respect to time. Okay, well, notice I've almost got dy dt by itself, so I've got that all of this thing, the left-hand side, the derivative of the left-hand side, is equal to the derivative of the right-hand side. So all of this is equal to 0. So 2x of t dx dt plus 2y of t dy dt is equal to 0. Well, let's go ahead and just solve for dy dt. So dy dt, subtract the 2x of t dx dt over, and then divide by 2y of t. This is going to be negative x of t over y of t times dy or dx dt. And I know I can go ahead and put the, well, we'll save that for step 5 of inputting this stuff. Okay, so here I've got dy dt almost, completely done here. I just need to figure out a few more pieces of information. So dy dt, this thing that I'm interested in, evaluated at t equals 1, let's just plug that in. So this is negative x of 1 over y of 1 times dx dt, but I know what that is. It's constant. It's 0.8 meters per second. Okay, well, how do I figure out x of 1 and y of 1? Well, I know that x of 0 is 1.5 and dx dt is 0.8 meters per second. So after 1 second, I will have moved over by 0.8 meters. So I know that x of 1 is equal to 1.5 plus 0.8, which is 2.3 meters. Y of 1 I can determine using, well, this relationship. I have the Pythagorean theorem, and I know x, and so I can certainly solve this for y. So I know that this is going to be equal to, if I move the x squared over and then take a square root, this is going to be equal to the square root of 25 minus x of 1 squared. And this is just the square root of 25 minus 2.3 squared. And you can do this on a calculator. I won't do it here, but this is approximately 4.44 meters. Okay, well, I've got x of 1, I've got y of 1, and I've got everything I need now to solve dy dt at t equals 1. So this is equal to negative 2.3 divided by 4.44 times 0.8, and by the magic of a calculator, which I'm omitting from actually writing down, but you can certainly do this yourself, this is equal to approximately negative 0.41 meters per second. And we're going to have a negative here because the ladder is sliding down, and we've sort of chosen the downward direction as the negative direction in our problem. And we're done. That's it. So I think this sort of 5-step process really helps with the organization of these problems. We identified and gave names to these quantities we're interested in. We noted that they depended on time. And we also wrote down some specific values of these and wrote down our final sort of end goal that we wanted. We found a geometric relationship between those quantities and then differentiated that relationship with respect to time, the independent variable, and got a relationship for the rates of change that we're interested in. And then we just used the information in the problem to determine all of the quantities that we needed in order to get our final answer right here. Okay, so that's kind of how these problems go. Let's do another one just to get some more practice. So another sort of classic example. So an observer uses a telescope to track a rocket launched vertically from a site 6 kilometers away, horizontally. Also, we're not up a slope or anything. We're just perfectly horizontally away. At a certain moment, we're not going to specify which moment, but at some moment, the angle between the telescope and the ground is pi over 3 radians, and is changing at a rate of 0.9 radians per minute. At this moment, how fast is the rocket traveling? Okay, so I've got this onlooker. He's looking at this rocket being launched, and his telescope is moving at a certain angle, and from that I want to be able to infer the velocity of the rocket. So, as per usual with these problems, let's go ahead and begin step 1. We'll draw our picture. So we'll put our little guy at the origin. We'll launch the rocket up. Wow, what an amazing rocket. You've never seen better artistic ability in your life. And then our onlooker is looking kind of along this line. His telescope is right here. This distance we know is 6 kilometers. And I know that this angle right here, I'm interested in that, the angle between the telescope and the ground. So we'll call that angle theta. And then if I want to know the velocity of the rocket, that's going to depend on the height of the rocket. So we'll call that height y. So theta is angle, y is equal to height. Won't be as verbose in the first problem. You can look here and see what they mean. So there's the variables, and there's a picture of what's happening. So what am I interested in? I'm interested in this dy dt. So let's write down what we know and what we don't know. So we know that theta is equal to, at this particular instant, pi over 3. And I also know that d theta dt at this instant is equal to 0.9. And what I want is dy dt at this particular instant, right? I'm interested in the velocity of the rocket, and so that's going to be precisely the rate of change of the height, which is dy dt. And again, we could note that theta and y are both functions of time. They are changing with respect to the variable time. Okay, so there's what we know and what we don't know. What's a relationship between these quantities? Well, notice what I have here. I again have a right triangle. I have two sides of that triangle and an angle in that triangle, so maybe a trigonometric identity would be good. And as I alluded to at the beginning of the lecture, we can use the identity for tangent. So the sort of thing that you learn in high school algebra or pre-cal or whatever is that tangent of theta is equal to the ratio of the opposite side and the adjacent side, so y over 6. And again, we have tangent of theta of t, just to reiterate the fact that these are really functions of time. And here I can write the divided by 6 as just times 1/6 right here. It's the same thing. Okay, so what's our next step? Let's differentiate. So dy, or not dy, or d dt of tangent of theta of t. I have to apply the chain rule, so I differentiate the outside function, secant squared theta of t. I plug in my inside function, and then I multiply by the derivative of the inside function. Same thing on the right-hand side, d dt of y of t over 6. This is just, well, 1/6 times dy dt, because I'm just computing directly the derivative of y. There's no sort of chain rule to apply. I'm just differentiating this function. Okay, so, well, that I'm almost done. I know that secant, the derivative of the left-hand side here, has to equal the derivative of the right-hand side. Well, if I just multiply by 6 on each side, I can isolate my dy dt. And so this implies that dy dt is equal to 6 times secant squared of theta of t times d theta dt. Well, I've got d theta dt. Oh, and look, I've also got theta. So we can just immediately solve the problem. So dy dt at this instant is 6 times secant squared of pi over 3 times 0.9. Secant squared of pi over 3, you can put this in on a calculator. It's equal to 4. So this is going to be 24, because 4 times 6 is 24, times 0.9. And this is another thing you can do on your calculator. This is 21.6 kilometers per minute. Okay? And we're done. Again, that's our final answer. So I think that this 5-step process is really helpful for organizing information and for sort of giving you a next step. I think if you just look at this and sort of think about how do you figure this out, it's a little bit daunting and it's not totally clear how to proceed. But if you follow these steps, then the problem becomes much more manageable and it breaks out into these individually very manageable pieces. Okay, the most challenging parts of the problem are, I would say, are coming up with this geometric relationship and then maybe computing the derivative properly. But this is just a careful usage of the chain rule, which is sort of, you just be careful about it and you can do it. And then here, this is usually, you can be informed for which geometric equation to use or what relationship to use by drawing a decent enough picture. And all of the examples that I'll give you in your homework or that we may talk about more, you'll be able to draw a picture here, and that should hopefully inform your intuition enough to come up with a geometric relationship. Okay, so that's it for this lecture. In the next lecture, we're going to talk about a very interesting property of differentiable functions called the mean value theorem, and this will have some nice applications to some things that relate to some other topics we looked at the beginning of the course, like the intermediate value theorem. Okay, so see you all in the next lecture.